today I'm just going to discuss some of the research we've been doing done at the USDA ARS Conservation and Production Research Lab relating to the NEFA CAP grant. And this is in collaboration with several of our AgriLife research in Amarillo. Most of this research is revolved around supplementation strategies for cattle on different forage diets. As I think we're all aware, greenhouse gas emissions and carbon footprints are of great interest to almost everyone nowadays. This is partly because of potential regulations, both federal and state regulations, also consumer concerns about their own carbon footprint, and retailers' requirements that the animals that they sell or products they sell come from sustainable systems. The primary greenhouse gas emissions we are concerned about from beef cattle, first is carbon dioxide, but that's just a normal product of metabolism and respiration and of fermentation of manure or from burning. Then methane, which most of the methane we see from the beef cattle industry is through fermentation within the digestive tract. Most of that occurs in the rumen and not in the lower gut. About 90 to 95% of that is in the rumen. And then we also have some fermentation of manure and plant materials which can produce methane. Another product is, or greenhouse gas, is nitrous oxide, which normally is 0 to 2% of the manure and nitrogen excreted, although we don't have really good estimates on those. But they can also come from soils and from fertilizers. There have been several scientists over the past few years that have done life cycle analyses of the North American beef industry, and pretty consistently they continue to find that about 70% of the greenhouse gases, and we normally express this as in CO2 equivalents, that's CO2e, and about 70% comes from the cow herd, about 17% comes from stocker operations, and about 13% comes from feedlots. This is a lot different than what most people believe. But there, about 87% of the carbon footprint comes from animals that are on grass. Primarily, most of that CO2 equivalent comes, or about 60%, comes from enteric fermentation. That's the production of methane in the rumen and the lower gut. That is about 20% comes from manure, and about 19% from energy and from secondary emissions. So if we summarize that again, so I mentioned these LCAs say that 55 to 63% of total greenhouse gas emissions from the beef cattle industry are enteric methane, and 84 to 88% come from cows and starter calves grazing pastures. We also have to remember that pastures and crops as well and soils can actually be sinks for methane and carbon dioxide as well. Now, enteric methane production of U.S. feedlot cattle may already be close to the biological minimum. It runs about 2 to 4% of the gross energy intake of the animals. And we get much lower than that, and we start having problems with fermentation within the rumen of the animal. So the greatest opportunity to decrease the carbon footprint appears to be in grazing cattle. And therefore, in the last several years, we've conducted a series of studies to examine the effects of supplementation on the emissions of from cattle grazing different forage systems. In the first study we did, we were looking at the effects of protein supplementation to steers fed a low-quality forage diet. And I should thank my co-authors here, Adam Schreck, who was a postdoc with us at Bushland, Eric Bailey, who's at West Texas A&M University, and Jenny Jennings with Texas A&M AgriLife Research in Amarillo. If you look at the chemical composition of forages that are growing, the pastures that are growing, this is a fairly typical of what you will see. When the plants are growing in the spring and maybe into the summer, we have for example, in this example, we're looking at the protein content. Protein content is up around 12 to 16%. However, during the winter, when the plant's not growing and when it's dormant and has been damaged by frost, the protein levels can get down to 4% or even less. Now, if we look at that yellow bars again, which are the crude protein of the range grass, and then look at the red bars, which are the protein requirements for a spring calving beef cow, we can see that during some parts of the year, primarily the spring and summer, the forage is adequate, has enough protein for that animal. But during the winter months, the protein in the forage is deficient and not enough for the animal's requirements. So it's very typical that protein is supplemented to beef cows and to starter calves when they're on these low-quality forages. That does several things. It increases forage intake, primarily because it increases the forage digestion and the utilization of that forage. In the starter cattle, it will increase weight gain, and in beef cows, it will increase the reproductive efficiency of the animal. However, we really don't know what this supplementation does as far as greenhouse gas emissions, and we don't know what the optimal quantity or source of supplement we need for methane mitigation. So in the first study we conducted, we used 23 British crossbred steers in 3 28-day periods. This was a crossover design, so all the animals were on all the treatments at a different period. The first 14 days of each period was for adaptation to the new diet, and the last 14 days was for data collection. And we did collect ruminal fluid by stomach tube on the last day of each period. These cattle were fed a low-quality blue stem hay in cow and head gates, so they had ad lib access. This forage was analyzed and contained 4.2% crude protein, which is well below the nutrient requirements of these cattle. If you're not familiar with cow and gates, this is a picture of our gate system where each animal is assigned one stall, and he can only eat from that one stall, and so we can get an individual intake from each animal in that pen. The supplement treatments we used, first we had a control diet or a negative control with no supplementation. Then we had a group of animals that were fed cottonseed meal at about 0.3% of body weight, and another group that was fed dried distiller's grains with solubles at about 0.4% of body weight. These different rates were fed because we wanted to feed the same amount of crude protein in both the cottonseed meal and distiller's grains supplements. Methane and carbon dioxide emissions were measured using a new green feed system. This is the composition of the cottonseed meal and the distiller's grains. In the areas I've highlighted here, you can see cottonseed meal is higher in protein than the distiller's grains. It's also higher in ruminal degradable protein, but distiller's grains are considerably higher in fiber and in fat and in overall energy value. This is a picture of the green feed system if you haven't seen one. This is another diagram. It shows where an animal puts its head into the feeder and it drops a small treat for the animal to eat. It identifies the animal, and while the animal is in the head gate eating, it's getting samples of air for methane and carbon dioxide analysis, and then measuring through some algorithms calculating methane and carbon dioxide production of the animal. In the green feed, the treat we used in this study was a pelleted cottonseed hulls. This is what it looked like. Again, we use this because these are very palatable, and because they're pelleted, they flow well through the system, and they're also low in protein, so they simulated the low-quality hay we were feeding. This is what happened to forage intake when we fed these animals. And control animals only ate about 3.7 kilograms, or about 7.4 pounds of hay, whereas when we provided cottonseed meal or distiller's grains, we increased that forage intake to up over 12 pounds a day in these cattle. If we compare this to other research data, we look along here, and it's ranged from a protein supplementation routinely increases forage intake anywhere from 27 to 121%. In our case, we were right at 53%, which is about in the middle of these values. We look at carbon dioxide production from each animal, and again, because of the higher intake when we fed the supplement, we increased the amount of carbon dioxide produced by the animals. from about 4,900 grams per day, excuse me, up to about 5,500 grams per day. But the carbon dioxide production per kilogram of feed intake was reduced about 30 to 40% when we provided a protein supplement, from about 1,300 grams down to less than 1,000 grams. Similarly, with methane, we saw an increase in total methane production when we fed a protein supplement. This again was primarily because we had a higher forage intake in these animals. But the amount of methane produced per kilogram of dry matter intake, again, was reduced about 20%, from about 47 grams, down to about 35 grams per kilogram dry matter intake. Similarly, if we look at what we call YM, which is methane production as a percentage of gross energy intake, in the control animals, that was over 10%. So over 10% of the energy in this forage was being lost as methane from these animals. So that was a bit, obviously an energy loss to them. But when we fed a protein supplement, we reduced that loss to less than 8%. And you'll notice, although it wasn't statistically different, the distiller's grains were a little bit lower than the cottonseed meal. We also saw, we plotted the forage intake versus YM, or the methane production per unit of energy intake, and we saw this negative relationship. Again, total methane production went up as we increased forage intake, but methane production as a percentage of energy intake went down, as you can see in this graph. And this is fairly typical of data that has been seen for many years, that as we increase the amount of intake, we decrease the YM value. Also, as I mentioned, we took rumen samples from these animals on the last day of each period and analyzed those for volatile fatty acids. And what we saw is the acetate propionate ratio decreased with protein supplementation, and again was lowest in the distiller's grain diet. And this lower acetate propionate ratio would go along with the lower methane production. So in conclusion, in this first study, we can say that providing a protein supplement to steers fed a low-quality forage increased dry matter intake about 53%, which agrees with a lot of other studies. Protein supplementation also increased total enteric methane and metabolic carbon dioxide production. Again, this was primarily due to the increase in forage dry matter intake. Protein supplementation decreased methane production as a percent of gross energy intake, or YM, and again, this agrees with the changes in ruminal fluid acetate to propionate ratio. And enteric methane YM decreased with increasing forage dry matter intake. Again, this agrees with classical data. Enteric methane production of the cattle fed distiller's grains was somewhat lower than that of the cattle fed the cottonseed meal. This is possibly because the distiller's grain had a greater fat intake, and we know that increase in fat intake will normally lower methane production, and also again because of a lower ruminal acetate propionate ratio, and because of the greater total digestible nutrients and metabolizable energy values of the distiller's grains. So we are also interested in what happens when we supplement animals that are on high quality forages. And in the southern Great Plains, there are millions of steers that graze wheat pasture each year, and this is a way of obtaining some relatively cheap weight gains on annual forages. But many times cattle are supplemented with some type of an energy supplement to increase average daily gain, increase carrying capacity, or extend the grazing period. And also there is some belief it may reduce the risk of a wheat pasture bloat in these cattle. So we conducted 2 studies to look at the effects of energy supplementation to steers consuming wheat forage, again working with people at Texas AgriLife Research and with Texas A&M AgriLife and West Texas A&M University. Again, as I mentioned earlier, energy supplementation to stocker cattle is fairly common. Gerald Horn at Oklahoma State University did an excellent review on this a few years ago and showed that when we provide a high energy the high digestible energy supplement to cattle on wheat pasture, we typically increase the animal's average daily gain by anywhere from 0.15 to 0.25 kilograms per day, or just from about 0.4 to over half a pound per day. And it increases the carrying capacity of that wheat pasture by up to 30%. However, again, as with other things, the effects on greenhouse gas emissions are not known. So in this first wheat pasture trial, we wanted to quantify the baseline greenhouse gas emissions of steers fed green chop wheat forage with or without an energy supplement. And then again to determine the effects of a corn-based energy supplement on methane production and energy metabolism of steers fed green chop wheat forage. In this study, we used 8 Angus crossbred steers that averaged about 206 kilograms in a replicated incomplete 4x4 Latin square with 3 periods in each Latin square. So we actually had 6 observations per treatment or per animal. Per treatment. The treatments were in a 2x2 factorial. The steers were fed the green chop wheat forage at either 1 time maintenance intake or at 1.5 times maintenance intake. And then they were fed a corn-based energy supplement at 0.5% of their body weight, or they were fed no energy supplement. But again, the reason for the 2 levels of energy intake is we wanted to see if we could calculate the net energy values for wheat forage. But for this paper or this talk, I will just be presenting the information on the 1.5 times maintenance data. The Latin squares, the periods in the Latin square were each 21 days in length. Again, the first 16 days were so animals could adapt to their diet in individual pens that were about 10 feet by 10 feet. And in the last 5 days, the animals were placed in one of 4 open-circuit indirect respiration calorimetry chambers. And during that 5-day collection, we measured gas exchange. That is, we measured oxygen consumption, carbon dioxide production, and methane production. And we also took total fecal production and total urine collection. The wheat forage was harvested 6 to 7 times per week using a riding lawnmower with a forage collection bin on it. The forage was harvested in the afternoon. Then it was stored in a walk-in cooler overnight and then fed the next morning. This is the composition of the supplement we fed. It was about half steam flake corn and mostly and wheat meds with a mineral supplement and molasses to help tie things together. The control animals did receive a mineral supplement that was made up of salt and limestone each day. This is what the respiration chambers look like. We pull air through these chambers, and then we measure the concentration of oxygen, methane, and carbon dioxide in the air going into the chambers and the air coming out. And by knowing the flow through the chambers, we can then calculate oxygen consumption and then methane and carbon dioxide production. The forage supplements, the forages, the supplements, the feces, and the urine are all analyzed for dry matter, organic matter, energy, nitrogen, carbon, and NDF. Again, the variables we measured were methane and carbon dioxide. We measured energy digestion and balance, carbon and nitrogen absorption and balance, and organic matter and NDF digestion. For those that aren't familiar with it, this is a schematic of typical energy metabolism in animals. We look at the diet going in is amount of energy going in is gross energy intake. We subtract the feces that's lost, and we get digestible energy. Then we subtract urine energy and methane energy to give metabolizable energy. And then heat production, which is measured from gas exchange and urinary nitrogen. And we subtract that, and what we end up with is retained energy or net energy for gain. This study was conducted in October through December of 2014. The average composition of the green chop wheat forage was about 44% dry matter, 20 to 25% neutral detergent fiber, and about 28% crude protein. And as I mentioned, only the data for the higher intake, 1.5 times maintenance, will be presented here. This is what the organic matter and neutral detergent fiber intakes look like. Of course, the organic matter intake was similar for both treatments, but this was by design, so there was no possibility for the supplement treatment to have an effect here. Again, NDF intakes were also similar for both diets. We look at the digestive organic matter, in neutral detergent fiber, and energy, and these were just pretty much the same. There was no significant difference when we supplemented the energy supplement with the wheat forage. Similarly, with nitrogen digestibility and urinary nitrogen excretion, we saw no effect from supplementing animals in this study, again, where intakes were limited to 1.5 times maintenance. The amount of nitrogen excreted in the urine is about 75%. That's very high compared to what we typically see, but this is just a demonstration of the high protein value that's in this wheat forage. Total methane production was reduced about 15 to 20% when we provided the supplement. Well, it's not statistically significant, but it tended to be different at P less than 0.06. And when we look at methane production per unit of energy intake, again, we reduced that from about 7 to less than 6%. Dietary energy values, when we provided the energy supplement, we did increase the overall digestible energy and metabolizable energy values of the complete diets, which you would expect since we were feeding the supplement contained higher energy value than the forage we were feeding. So we conducted a second study to quantify the baseline methane emissions and energy metabolism of steers grazing late season wheat pasture. We actually wanted to do this a little bit earlier, but because of several conditions, we were not able to get this started till late in the year. So this would be more like a wheat graze out situation. We also wanted to determine the effects of energy supplementation on methane emissions and energy metabolism of, again, steers grazing late season wheat pasture. In this study, we used 13 Angus crossbred steers that weighed about 400 kilograms. We used a 2-period crossover design. Each period was about 30 days in length. Animals had ad lib access to limitly irrigated wheat pasture, and I think this was irrigated to help get it up, and that was the only irrigation. We had 1.2 steers per hectare that averaged during the trial. All these animals were on the same pasture, and they were individually fed each day. They were brought up into pens and then individually fed. The control group received 200 grams of pelleted wheat mids. This was primarily because this was the carrier for our digestibility marker, titanium dioxide. Then the treated animals received a corn-based energy supplement at about 0.5% of their body weight, and this was adjusted every 30 days, and plus the 200 grams of pelleted wheat mids supplement. The animals also had ad lib access to salt blocks. This is the composition of the two supplements. The control supplement, which again was 87% wheat mids, 5% molasses, and 8% titanium dioxide. And then the energy supplement, which was wheat mids, dry rolled corn, and again molasses. At the end of each 30-day period, we collected feces from the animals for 6 days. These animals had been dosed or were dosed with titanium dioxide in the pelleted wheat mids for 10 days before the start of this 6-day collection. Forage samples were also taken from the pasture by hand clipping, and this was used to determine the in vitro dry matter digestibility of the wheat forage. And using, those of you may be aware or not be aware, by using the titanium dioxide marker and knowing the in vitro digestibility of the wheat forage, we were able to calculate a fecal output and forage dry matter on each of these animals. Again, the methane and carbon dioxide were measured using the green feed unit again. For this, we could not collect urine, so we assumed the urine energy loss at 1.4% of gross energy intake. And then heat production was calculated using the equation of Brouwer, assuming a respiratory quotient of 1.05. By that, that's the CO2 to oxygen ratio. And because we knew what the CO2 production was from the green feed system, we could use this 1.05 RQ ratio and then estimate the amount of oxygen that was consumed. Again, this is the energy metabolism scheme again. If you notice a little bit different, fecal energy was estimated using fecal output from the titanium dioxide marker. Urine energy was estimated as 1.4% of gross energy intake. Methane energy from the green feed, and then heat production was estimated from CO2 and O2 using the Brouwer equation. We measured, the data were analyzed, the performance, digestibility, gas emissions, and energy metabolism data were analyzed as a two-period crossover design with animals as the experimental unit. This is the composition of the wheat forage. You will notice the crude protein value was about 21% during period 1, then dropped to 15 during period 2. And similarly, the fiber contents increased slightly. So the wheat was maturing and starting to mature here. And so it's a lower quality than in the first experiment and was a lower quality in period 2 than in period 1, which you would expect. This is the total dry matter intake and forage dry matter intake. Total dry matter intake, again, when we fed the energy supplement, that was increased about 4 kilograms per day. That was a significant difference. Similarly, forage intake was increased by about 2 kilograms per day. As a percentage of body weight, forage intake increased from about 3.2 to about 3.6% of body weight when we provided the energy supplement. As in the first trial, the digestibility of organic matter and neutral detergent fiber was not significantly affected by our supplement. And again, this might not be expected because the wheat forage is a highly digestible forage. CO2 production was increased, tended to be increased by providing the energy supplement. Again, as a total went from about 9.8 up to 10.5 kilograms per day. However, as in the first trial, the carbon dioxide production per gram of dry matter intake was decreased from about 6.8 down to about 5.8. Again, methane production, megacalories per day, was not significantly affected, but methane production is a percentage of gross energy intake. This is very similar to the first trial, decrease from about 8.2% of energy intake down to about 6.4. This difference was statistically different. Again, heat production, which we calculated, was tended slightly to be slightly higher in the animals that were supplemented. Again, this was primarily due probably to the higher feed intake, but as a percentage of gross energy intake, heat production dropped from about 48% of energy intake to about 38% of energy intake. If we summarize these two wheat pasture trials together, we can say that corn supplement in the first trial, corn supplementation at 0.5% of body weight did not influence digestibility of organic matter, energy, or NDF. In the second trial, we had very similar results with no effect on fiber or organic matter digestibility. In the first trial, methane production as a percentage of gross energy intake was decreased about 16% with corn-based energy supplementation. In the second trial, again, a very similar decrease of about 21% when we fed a corn-based energy supplement. Again, methane production per unit of organic matter intake was decreased about 18% in the first trial and was reduced about 20% in the second trial. In trial 1, I didn't present this data, but the heat production as a percentage of gross energy intake was not affected by energy supplementation. But again, remember, these steers were limit fed the green shop wheat, did not have ad lib access to their forage. However, in the second trial, heat production as a percentage of energy intake was decreased about 20% with the corn-based energy supplementation. Now, again, as I mentioned earlier, Floyd Horn showed that feeding energy supplement to cattle on wheat pasture increases average daily gains about 0.15 to 0.2 kilograms per day. So if we assume the average daily gain of these cattle was about 0.9 for the control cattle, or about 2 pounds per day, and up to 1.05 or about 2.25 pounds per day for the control and supplemented steers, then if we make that assumption, then methane production per kilogram or per pound of average daily gain was decreased by over 30% when we fed an energy supplement to these cattle on wheat pasture. So I think we can summarize that energy supplementation offers potential to decrease methane emissions of cattle raising high-quality wheat pastures, and the effects of supplement composition and forage quality, however, need to be further evaluated to really look at if we can get more detail on how to lower these emissions. In summarizing, I think we can say that common practices that are being used by producers can decrease methane emissions and presumably the carbon footprint of beef production. However, we need additional research to examine the ways to optimize or increase this response. This may include how much fat is in that supplement, the starch, the digestible fiber, the use of ionophores, and there are some new potential methane inhibitors that may be coming on the market in the next few years. Also, factors such as grazing management and forage quality are going to have a major effect on this as well. With that, I want to thank the National Institutes of Food and Agriculture for their help in funding partially funding this project. With that, Amber, I think I can take questions.
Okay, we will give people a little bit to submit some questions while we're waiting to see if anybody else has one. I do have one for you, Andy, and that's, you talked about at the very beginning, you mentioned that we might be close to the metabolic minimum possible methane emissions from cattle in the U.S., and I was wondering, in terms of sort of global beef production, would this sort of a supplementation strategy, you think, dramatically reduce emissions in other countries or in different sorts of production systems? Do you think it's feasible in those sort of contexts? Okay,
well, first, I would say I may have misstated that I was talking about in feedlot situations where we may have reached close to the minimum, because methane production in the rumen is a normal byproduct of the fermentation of carbohydrates. It occurs in cattle, it occurs in elephants, it occurs in buffalo, it occurs in all wild ruminants, sheep and goats as well. So it's a natural byproduct, that fermentation. If we shut off that mechanism to produce methane, metabolites start backing up in the rumen, and the rumen stops functioning properly. So we do need some of that methane production for it to be working at its optimal condition. As far as the second part, these supplementation strategies help other parts of the world? I think similar strategies should have the potential. Of course, we talk about other parts of the world. We can be talking about New Zealand, where they have nice green grass almost 12 months of the year, or in Great Britain and Ireland, or we can be talking about desert areas in in other countries, for example, where it's much more limited, or where there's not much corn or protein supplement to provide these animals. And again, that's the major part. What kind of supplements do these other countries have to provide animals? Again, most of our supplements, for example, protein supplements, are actually byproducts of other industries. Cottonseed meal and soybean meal are byproducts of the making of obtaining cottonseed oil and soybean oil. And luckily, they're good products to feed the livestock. And some countries have these products and some don't. I hope that answered your question.
Yes, it does.
I think the mechanism has the potential, if the resources are there, for these countries to be able to do that.